Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Imagine a creature so small it's invisible to the naked eye, yet possessing a sense of direction so precise it navigates using Earth's invisible magnetic field. Now, imagine this creature on Mars, utilizing the planet's weak, residual magnetism not just to find its way, but to locate its food source, solid iron ore. This is the premise of the Magnetotactic microbe trap, an ingenious hypothesis suggesting how life, if it ever existed on Mars, may have managed to eat the very rocks of the red planet. To understand the Martian trap, we must first look down, deep into the mud and sediments of Earth. Here, we find magnetotactic bacteria, or MTBs. These remarkable microorganisms operate on a simple principle. If you need to access a specific chemical zone in the water column, usually the boundary between oxygen-rich and oxygen-poor layers, called the oxic-anoxic interface, OAI, you need a highly efficient guidance system. They found one in internal geology. MTBs synthesize tiny, perfectly formed crystals of magnetite, Fe3O4, or greigite, Fe3S4. These nanoparticles, called magnetosomes, are aligned like a microscopic string of pearls within the cell, acting as a permanent magnetic dipole, a biological compass needle. They don't navigate the globe. They simply follow the magnetic field lines downwards or upwards, depending on their species, leading them directly and efficiently to their preferred low-oxygen habitat. It's biological GPS optimized for survival, saving them vast amounts of energy. But Mars is vastly different from a terrestrial swamp. Today, Mars lacks a global magnetic field, relying only on residual, localized magnetism locked in ancient crustal rocks. Furthermore, Martian microbes wouldn't just be looking for a chemical interface. They would need to actively extract energy from inorganic compounds, specifically the massive deposits of iron ore that give Mars its famous red hue, like hematite and magnetite. This is where the trap mechanism comes into play. Metabolism is expensive. Dissolving solid rock, particularly iron ore, is energetically intensive. If a Martian microbe evolved to be a litho-autotroph, a rock eater, it would face a critical energy budget problem. It cannot afford to wander aimlessly across the Martian regolith looking for a suitable vein of iron. The environment demands hyper-efficiency. The solution, according to astrobiologists, lies in optimizing the initial search. On Mars, iron deposits often correspond precisely with the zones where the localized remnant magnetic fields are strongest. These fields are literal signposts. A Martian MTB would evolve to use its magnetosomes to follow these localized fields, leading it directly to concentrated pockets of hematite or magnetite ore, where the required chemical feedstock is guaranteed. Instead of being merely a byproduct of iron sequestration, the magnetosome synthesis becomes an integral part of the rock-eating machinery. The microbe utilizes the geomagnetic gradient as a homing beacon to maximize its exposure to the very minerals it needs to digest. The magnetic field essentially funnels the organisms into the iron veins, the magnetotactic microbe trap. When we look at the samples returned by rovers like Perseverance, a key goal is finding magnetofossils, the preserved remnants of these ancient magnetosomes. These crystals are chemically and physically distinct from iron oxides formed by non-biological processes. If we find these perfectly ordered, uniform magnetosomes embedded in ancient Martian sediments, it would constitute one of the strongest possible biosignatures. It would tell us not only that life once existed on Mars, but that it evolved a highly sophisticated, magnetic field-guided mechanism to thrive by consuming the planet itself. The potential discovery transcends microbial life. It fundamentally changes our understanding of planetary habitability. It means life can weaponize the weakest physical forces of a planet, using invisible magnetism to turn solid rock into sustenance. The red planet may be painted with iron, but if these microbes were real, they were using that iron as a microscopic compass guiding them straight to dinner. For more incredible facts like this, don't forget to subscribe and turn on notifications.